Hello everyone, welcome to my poster presentation. My name is ZIPENG Guo. I'm a PhD student. Dr. Zhizhou is my advisor. Here we want to present our work on the experimental and analytical study of additive manufacturing of multi-scale porous silica aerogel for thermal insulation. As we all know, heat dissipation or diffusion is the nature of thermal energy. Therefore, we always want to reduce the heat transfer or heat loss such that we can reduce the energy waste and improve the energy efficiency. And talking about the thermal insulation, it couldn't be more important during the winter time. One of the thermal insulation materials, the silica aerogel, has intrinsic low thermal conductivity. However, the cost of fabrication the silica aerogel is very heavy in terms of time cost, equipment cost, and energy cost. Therefore, a cost-effective and scalable manufacturing technique is highly desirable. To conquer this challenge, nature actually provides exceptional guidance. Most of the biological creatures have internal porous structures. These porous networks undergo evolution after evolution that span centuries of time. For example, the trunk of trees has multi-scale, hierarchical, and optimally arranged porous networks, leading to multifunctionalities such as nutrition transfer and outstanding strength. To mimic the nature-inspired multi-scale porous structures, we used the foaming agent to prepare the 3D printable material. It is very similar to the detergent that we used for washing and cleaning. The foaming agent can create air bubbles in the printable materials, and after 3D printing and ambient drying, the air bubbles convert to empty pores. Then we can obtain the silica aerogel in three-dimensional porous structures. Additionally, we performed the simulation studies to explore the physical phenomena during the printing process, and the simulation results in turn provides us insights to optimize the printing process towards high resolution and high shape fidelity printing. Moving on to the results section, I want to first present the novel multi-scale porous structures. From the macro scale to micro scale and eventually the nanoscale empty pores can be created. Such a multi-scale porous network is the key for thermal insulation. These empty pores can confine the air molecules inside the voids and restrain the heat transfer. Our experimental results verified that using the foaming agent can significantly reduce the thermal conductivity. And on top of that, to ensure the durability of such very porous samples, we further explored adding fiber to reinforce the mechanical strength. Here is a demonstration of the thermal insulation property of a 3D printed UV logo made of silica aerogel. We put the printed UV logo on a very hot surface and took this infrared image. The background color is very light, indicates the temperature of the bottom surface is very high. While looking at the UV logo, the top surface, it has a much darker color, indicates the printed UV logo can insulate the heat, and thus the temperature on the top surface is very low. Having successfully printed the multi-scale porous network, we further performed the computational fluid dynamics simulation to optimize the printing process, such that we could achieve better printing resolution and shape fidelity. Our own nozzle design showed that the curved edge facilitates the material flow by mitigating the stress concentration, and the flow velocity can gradually increase at the necking region and the nozzle region. In addition to that, we can see a steady velocity at the nozzle outlets. All of these results guarantee that the high printing resolution can be achieved. To summarize, we demonstrated a low-cost and a scalable additive manufacturing process for producing multi-porous network, and compared to the commercial products, our printed silica aerogel has the best thermal insulation performance. We believe that these results could further motivate developments in the 3D printing field, and more importantly, in the future, we will expand this additive manufacturing process to larger scale and various materials. Thank you for your attention and looking forward to any questions and suggestions.